Okay, ladies and gentlemen, so hopefully you have already listened to my lecture on Hardy-Weinberg and now you're getting on into the practice problem set. It's just good to be able to practice it and go over it. This is really algebra. Okay, that's really all it boils down to. I know that makes some of you want to cry and cringe inside, but that really is what this is. So before we get started, I always write my two equations, p plus q equals 1, and p squared plus 2pq plus q squared equals 1. Now, I guess you guys can count your lucky stars because due to the pandemic, you guys don't actually have to memorize those equations. So I have sampled a population in which I know that the percentage of the homozygous recessive allele, little a, is 36%. Using that, calculate the following. So the frequency of my little a genotype, that's what it wants to know first. Well, little a, which is also known as q squared, is equal to 0.36. That's what our 36% is. Now, if you're good at mental math, great. If not, you can always use your handy dandy calculator. What I want to know then is what the square root of 0.36 is. So I'm going to type that into my calculator, and that means that A, which is equal to Q, is 0.6, okay? Then the frequency of the big A allele. This case, I'm going to use P plus Q equals 1. In this case, P plus Q, if I go through and I rearrange that, I'm going to do P equals 1 minus Q, which is 1 minus 0.6, which equals 0.4. And when you get to your homework, you'll notice that I ask you to like circle or put a box or something around your actual answers. This is what I'm talking about. Back to elementary math, just make my life easier. So now I want to know what the frequency of the homozygous dominant and the heterozygous are. So in order to get the homozygous dominant, AA, this is going to equal P squared, which is 0.4 squared, which is 0.16. And then my big A little a is 2PQ, which equals 2 times 0.16. Sorry, no, wrong thing. Is going to be 2 times 0.6 times 0.4, and that is then going to equal 0.48. So, and then if I go through here and I add up 0.48 plus 0.16 plus 0.36, I actually get 1. That's a good way to double check your work. Also, just so that you are aware, you can, sometimes it will be 0.98, sometimes it will be 1.02. I accept a margin of error usually about 0.02 because of rounding. Sometimes things don't come out evenly. Some people might round up, some people might round down. You are going to get slightly differences there. Now, the frequency of the two possible phenotypes, if A is completely dominant, big A is completely dominant over little a, okay? So I'm going to expect the dominant phenotype is going to be 0.16 plus 0.48, okay? Which is then going, to be equal to 0.64. And then my recessive is 0.36. And again, that very nicely adds up to 1, but not that that is an absolute necessity. It could be slightly different. Okay, I would like to do one other with you guys. This is not broken down quite as nicely as the previous one, but it's another example of what you guys are going to see. So we see sickle cell, right? We feel that sickle cell is as prevalent as it is because it's a heterozygous advantage. Those who are heterozygous for sickle cell don't contract malaria, but they don't die of the disease all over entirely. It is actually technically a codominant disease. So when you have sickle cell, if you're a carrier for sickle cell, approximately 50% of your red blood cells are indeed sickle shaped. So I'm saying that if I have 9% of my population is born with the severe form of sickle disease, okay, then I want to know what percentage is going to be more resistant to malaria because they're actually heterozygous for it. So little is going to equal Q squared, which is 0.09. Okay, so Q is then going to be, I take the square root of that, 0.03. Okay, P is going to equal 1 minus Q, which is 1 minus 0.3, which is going to be 0.7. So 2PQ, which is my heterozygous population, is 2 times 0.3 times 0.7, which is then going to be equivalent to 0.42, which is my final answer, okay, that they are more resilient to malaria because of that. You have the sheet. On the sheet, there are other examples. I just wanted to go through the first two with you guys. If you have questions about it, please reach out to me or bring them to one of our Zoom sessions and we can go over it. Thanks.